Have you ever just stared at your computer and wondered what is actually going on in there? What is it thinking? Well, today we're going to crack open that case, metaphorically, and go inside the machine's brain to figure out how billions of simple little switches create the entire complex digital world that we all live in. And let's be honest here. For a lot of us, what happens inside a computer might as well be magic, right? It's just this box that either works or it doesn't. And when we hear it's made of millions of tiny on and off switches, that doesn't really help. In fact, looking at this little guy right here, it can sometimes feel like our own brain just switches off when we even try to understand it. So that really is the big question, isn't it? How do you get from a simple on or off, a 1 or a 0, to streaming movies, to calculating rocket trajectories, to literally running our entire world? Well, the answer starts with the two components that sit at the very heart of the machine. Yeah, it all begins with two core components that do pretty much all of the heavy lifting. You've got the central processing unit, which you've probably heard of as the CPU, and you've got memory. The easiest way to think about it is this. The CPU is the computer's brain, and memory is its short-term memory. They're constantly talking to each other, working together. Now, to really make sense of how they work together, we're going to use this absolutely brilliant analogy called the little man computer. It's really just a simple story, but it is the perfect way to explain the fundamental operations of a real super complex machine. So I want you to picture a tiny man in a mailroom. This room has 100 mailboxes on the wall, numbered 0 to 99, and they're used for storing information. That's our computer's memory. On his desk, the little man has a simple calculator for doing all the math. We're going to call that the arithmetic/logic unit. To keep himself organized, he has this little location counter that clicks up one by one so he always knows which task to do next. And then, of course, there's the little man himself. His whole job is to run around fetching instructions from the mailboxes and carrying them out. He is the control unit. He is the one running the whole show. Okay, now here is the really cool part. This whole mailroom story, it's not just a cute little analogy. It actually maps almost perfectly onto the real high-tech components that are sitting inside your computer right now. Let's take a look at how that translation actually works. You'll see the connection is just so direct, it's amazing. The little man, the guy running the show, that's the control unit in a real CPU. The mailboxes on the wall, that's the computer's memory, or what we call RAM. The calculator he uses is the arithmetic/logic unit, or ALU. And that location counter on his desk, that is the program counter. See? It's this perfect one-to-one relationship between our simple story and the actual hardware. All right, let's zoom in even closer on the CPU itself. To work as fast as it does, it uses these tiny, super fast little storage spots called registers. The absolute best way to think of these is as the little man's personal notepad. You know, he can quickly jot down a number or a mailbox address or the instruction he's currently working on. They're just for temporary stuff, but they are absolutely essential for making everything happen at incredible speeds. And what's really crucial here is that different notepads, or registers, have very specific jobs. For instance, the program counter is his what's next notepad. It always holds the address of the next instruction. The instruction register, well, that's his what am I doing right now pad. Then you have the accumulator. That's just a general scratch pad for doing math. And finally, the MR and the MDR, they work together like the to and from addresses you'd write on a package, telling the data exactly where it needs to go. So with all those components in mind, we can finally understand the computer's most fundamental routine. It's this core process called the fetch-execute cycle. And it is, quite literally, the heartbeat of every single thing your computer does. You know, it seems almost too simple to be true, but it's not. No matter how complicated the task is, whether you're editing a 4K video or your computer is flying a fighter jet, its entire existence boils down to this endless two-step dance. Step 1, fetch an instruction from memory. Step 2, execute that instruction. That's it. It just does that over and over and over, billions of times every single second. So let's just quickly trace a single simple command, like load, which just tells the computer to go get some data. During the fetch phase, the CPU uses the program counter and the MAR to figure out where the instruction is and pulls it into the instruction register. Then, during the execute phase, it decodes that instruction, grabs the actual data it needs from memory using the MAR and MDR, and puts it in the accumulator. And the very last thing it does is add 1 to the program counter so it's ready for the next command in line. It's this precise, beautiful flow of information between all those little notepads. And, as the source material so perfectly puts it, there's a real elegant simplicity to this whole thing. That load command we just saw, it only takes 5 steps. Every complex program you've ever used is just built from millions and millions of these simple, foundational operations, all happening one after another at lightning speed. Okay, so we've got the brain, we've got the memory, we've got the core routine, but how do all of these different parts actually talk to each other? How does the information physically get from point A to point B? Well, that's where something called a bus comes in. A bus is basically the information superhighway inside your computer. It's nothing more than a set of physical wires, these little electrical pathways, that connect everything together. The CPU, the memory, your graphics card, they all use the bus to send and receive data. Now, way back when, computers used what were called parallel buses. Think of a massive 64-lane highway sending tons of data all at once. It was fast, but it was also expensive and could get kind of messy with interference between the lanes. Today, most of the connections you use, like USB, are a serial bus. Think of that as a super efficient single-lane express route. It sends data just one bit at a time, but it does it so incredibly fast and reliably that it's actually the standard for almost everything now. So what's actually zipping along these highways? Well, it's more than just the information itself. Of course, you have the data. But you also have an address, which is kind of like the zip code that tells the data where it needs to go. Then you have control signals, which act like traffic lights, managing the flow and timing of everything. And finally, you have the power lines, which provide the electricity to make the whole system work in the first place. So there you have it. We went from a simple little story about a man in a mailroom all the way to the real architecture of a modern computer. And the biggest takeaway here is that all of this incredible complexity is really just built on layers and layers of very simple, very logical principles that, honestly, haven't changed all that much in decades. And that kind of leaves us with a really fascinating question, doesn't it? This core fetch-execute model, this one-step-at-a-time mailroom process, has been the absolute foundation of computing for more than half a century. But as we keep pushing the limits of speed and power, you have to wonder, is there a better way? What will it take to create a computer brain that doesn't just execute a list of instructions, but that thinks in a fundamentally new way?